So let me remind you of some of the notions that Monica presented to us yesterday. So what we consider here are valuations on the space conv Rnr, which will later be the space of convex functions in Cn, that take only finite values. So there are not value plus infinity is not allowed. And we consider this as a topological space with respect to the topology of locally uniform convergence. Then if you have a abelian semigroup, then functional on the space with value in the semigroup is called valuation if you have this kind of decomposition property. So we take the functional on the maximum of the two functions and on the minimum of the two functions, and this should be the same if you add it together than if you do it separately on the function. And of course this should hold whenever both sides of this equation are well defined. So the going example will be some type of Monge-Amp ere-type operator. So for example, you can look at the Hessian measures that we saw yesterday, which for smooth functions are given by integrating the case elementary symmetric function of the eigenvalues of the Hessian over a given Borel set. And in the general case, you can extend this by continuing. Now, one thing to realize is that all of these functionals are, of course, invariant if you add some affine function to your convex function, because they only involve the Hessian. And this property is called dually epi-translation invariance. And yesterday we saw why this is the case, where this notion comes from. It's related to translation invariance of the epigraph in the dual setting when you go to the Lagrange transform. So I want to give this space of functionals a name. So I will denote by vconv, valuations on convex functions, the space of all continuous and dually epi-translation invariant valuations that take real values on the space. And this is a very interesting space, and it has a lot of structure. And for example, if you look at k-homogeneous valuation, so where you just define a valuation to be k-homogeneous as property with respect to the usual multiplication, then the space decomposes into a direct sum of n+1 components of homogeneous valuations. So in other words, you can express every arbitrary valuation in this class as a sum of n+1 homogeneous valuations, which greatly simplifies characterization results. So the second thing I want to remind you is this Hartwig type theorem for valuations on convex functions. Namely, if you look at S or n invariant valuations in this class, and so it's restricted to the degrees between 1 and n-1, then valuations S or n invariant if and only if there exists some density function in the right class of functions such that you have such an integral representation. And the densities, they have to be continuous on the positive real line with support bounded from above, but they can have a singularity that is controlled by these two equations down here. Now the way I've written it here, this is plainly wrong, because the integral is usually not well defined. This function that you see there is not integrable in general with respect to the Hessian measures. But if you take a principal value, then this is well defined. So that's the Hartwig result, and you can see this somewhat very much resembles Hartwig's characterization of the intrinsic volumes, except that now you don't just have one intrinsic volume per degree of homogeneity, you have a whole family, and the family is indexed by these density functions. Now, Hartwig type results don't only exist for the group of all rotations, but for other complex subgroups as well. And in fact, we have basically a complete characterization when you can expect such a nice finite dimensional Hartwig type result to hold. Namely, if you take any compact subgroup of the group of rotations, then the space G of all continuous translation invariant valuations on convex body in Rn that are also invariant under the group is a finite dimensional space if and only if your group operates transitively on the unit sphere. So in this case, you can have nice Hartwig type results. You just have to find the right basis to express your space of valuation in. And in fact, there aren't all that many groups. Well, there are infinitely many of them, but essentially there are only 6 infinite series. So we have the group of rotations and then certain complex groups, and then these symplectic groups, and then in addition 3 exceptional groups. And in all of these cases, people have looked at the corresponding space of invariant valuations, and in most cases we have complete classifications, and in all cases we know at least what the dimension of these spaces are. Now, if we want to now go to the functional setting again, then you could ask, what happens in all of these situations? What happens for these groups? Do we also have these Hartwig type results? And so let's start with the easiest next case after SON, namely UN. And the question is, what happens? What can you expect there to happen? So the first to calculate the dimension of the space was Alaska in 2003, and he also gave several bases of the space. And some years later, Bernig and Fu, in the study of kinematic formulas in Hermitian integral geometry, they introduced several new bases, and one of them is the other so-called Hermitian intrinsic volumes. And these are characterized by a certain vanishing property under restrictions to special subspaces. So, what was the pointer here? This is the pointer. So what you do, you restrict the valuation to a subspace EKP, and you either get the volume on the subspace, or you get 0. And these spaces basically have 2 parts. You have a purely complex part, and then a purely real part that just fills the space up, so you have a k-dimensional space. So, for valuations on functions, there exists a very nice way to construct suitable analogs of the Hessian measures that have more general invariance properties. So for a C2 function, you can look at the graph of the differential of this function and consider this as a submanifold of the cotangent bundle. And this is an n-dimensional manifold, and it means that you can integrate suitable differential forms over it. So this defines an n-current. For general convex functions, which might not be smooth, this construction still extends as a functional and differential forms, as a current, which gives rise to the so-called differential cycle, which was introduced by Joe Fu. And what you can do with this graph cycle is you can now construct measures on, let's say Rn, by integrating this differential form that you're given over the part of the graph that lies above a given Borel set in Rn. And this is well defined for bounded Borel sets, and in fact you get a continuous valuation on the space of convex functions with values in the space of signed measures. So let's apply this to some nice invariant differential forms in the complex case. And so you can go to the complex tangent bundle and look at these 3 forms, which you don't have to look at in detail, this is just a formula. But you have 3 2 forms, so now you can look at all possible combinations of those, and these will give rise to suitable Monge-Amp type operators. Yeah. Very nice. What are those? Well, in general, you can write down the formula, what they are, but it's not really clear what they mean. But for certain degrees, you just get operators that you already know. So you get the Lebesgue measure and the real Monge-Amp operator, where you just integrate the determinant. But in the middle degree, you also get complex Monge-Amp operator, which is just given by integrating the complex determinant of the so-called complex Hessian. Now these measures are not quite enough for our purposes because there are more differential forms, and in fact there are 7 forms that are relevant, and I've written them down here and the interpretation when you restrict them to the graph. But you can now take basically any non-trivial product of this form and get some invariant Monge-Amp type operator. But of all of these forms and combinations, I only want to look at one additional family, namely this one, which, because I ran out of letters, is now called upsilon. So basically we now have 2 families of Monge-Amp type operators, which are indexed by k and q. So why precisely these 2 families? Well, the first reason is that they almost give you everything that you want. In the sense that when you look at valuations that you can construct from these operators by integrating in rotation invariant, let's say, smooth functions, you get a dense subspace of the space of all UN invariant valuations. And here, this space of valuations is equipped with the topology of uniform convergence of compact subsets on the space of convex functions. So, which is here the natural topology considered a space of continuous functions. The second reason why I don't use other combinations of these operators and take basically a different basis of this space is that they behave very nicely with respect to similar restrictions, similar to the intrinsic volumes. When you plug in functions that are defined on these spaces EKP of the wrong complexity degree, you can put them back by the orthogonal projection and plug them into these measures, then they vanish identically. So in other words, you can separate these measures by this property, and for every index cube, you now have two independent measures that you're dealing with. So this almost gives you a complete classification, except that you somehow need to take the closure from this dense subspace. And as for the functional intrinsic volumes, we would expect that there are probably certain singularities that occur. So the question is how can you get the corresponding singular valuations from these measures? And one way to do this is to try and estimate and see what happens when you just look at continuous functions. And you get expressions of this type. So if you integrate such a rotation invariant function, continuous with respect to these measures, you get two inequalities that look very similar. You have one term that is basically uniform in f, and you only need the values of f on a neighborhood of the support of the function that you're integrating, and then everything else is hidden in these two quantities here, which are written as two norms on the space of continuous functions, and these are given by this expression here. So when these inequalities look very similar, you can see here that the norms that you get on the right, they are very different. So for the first norm, we have the two terms that also occurred for the classification of SON invariant valuations, whereas for the second family of measures, you get something that's slightly different and probably simpler. You don't have this basically slightly non-local term here. So how do we get from this to the corresponding valuations? Well, I want to, let's start with the first one. I want to look at the map that integrates a given density and gives me the corresponding valuation. We call this map T. And now the estimate that we had before, this gives you basically an estimate for the operator norm of this map. So we have here an estimate with respect to this norm. So the question is, what is the maximum extension that we can have now? Well, we can complete the space of continuous functions with respect to this norm. And if you do that, and you restrict yourself to functions with support contained, let's say, an interval from 0 to r, then these spaces from the classification of SON invariant valuations, they are just the completion of these, of the space of continuous functions with respect to these norms. So in other words, what you get, because the space of valuation is complete, is that you get some map, continuous map from the space of density functions to the space of valuations, such that whenever you have a continuous functions, you just get the usual integration. Now, this is not quite what you want. This doesn't only gives you a very indirect way to actually access these functionals, but using the estimates from the previous slides, you can actually get that this expression here is in general just given by a principal value. So this is the first family of measures. What happens for the second? Well, you can actually get something slightly better than before. You can get an estimate on that of the variation of your measure. So this now gives you not only such a principal value type representation, but actually some integration formula. So from this, you can divide this expression there just by the appropriate power of z, and then you get that this function here is integrable with respect to these measures. So in particular, for any continuous function psi, this expression gives you a well-defined valuation. However, there's a bit of a catch. This function is only continuous when the function vanishes in 0. And in all other cases, it is not continuous. Now, why is this the case? Well, I can tell you why functionals are continuous when they vanish in 0. And this is also due to some completion phenomena. So if you now take a space that is adapted to this norm from the previous slide, in the sense that you have all, again, continuous functions with bounded support, and here you take this appropriate property here that it converges to 0 when you set t to 0, the correct power, then this space is the completion of the space of continuous functions under suitable support restrictions with respect to the norm that we had in the inequality. So now, if you take one function in the space and you define this corresponding valuation by just integrating this function with respect to the corresponding measure, and now this is actually an integral because it's integrable, then this function is well defined and continuous. Consider the map from the space of densities to the space of valuations. And well, it is continuous because of the estimate, and it's well defined because it's well defined for continuous functions, and this is just the completion of this operation. So now we have the two types of valuations, and this gives you actually the complete classification. So every UN invariant valuation in this class can be written uniquely in terms of these two families of valuations. So what this looks like is basically in every component that we had, we pass to the closure separately, which is very nice. Yeah? So, but this is a bit strange. So first of all, if you look in the middle dimension, then actually you have around n different families of valuations that you have to deal with. And the goal would be to prove this result somehow by approximation, but when you have such a decomposition, then usually if you try to approximate something, you only know that the sum of all of these terms converges. This does not tell you anything about whether the components converge or not. So what you actually are doing here is, in background, is that you have some kind of decomposition going on. So recall you that these measures vanish on these special subspaces of lower dimensional convex functions with the wrong degree of complexity. And so what you can do is you can look at the space of valuations that have exactly this property, that they vanish on all of these subspaces except for the subspace with index q. And all valuations constructed from the theta and epsilon measures, they of course have this property. So what this classification result on the last slide actually states is basically that you have a decomposition of the space of all valuations into these components. And these components are closed subspaces, and you can show that this decomposition is actually dense and direct. So you have a sum of closed subspaces that is dense, but the problem is that the sum of closed subspaces does not need to be closed again. So this does not give you the decomposition outright. So what you actually have to do is show something slightly stronger. You have to show that this decomposition exists and that the corresponding projections are continuous. Because if you have this, then now when you have the continuous projections, then you know that all of the components converge. And this allows you to prove this result by induction. So in the last few minutes, I want to give you a short sketch of the proof. It's only 2 slides, so not too many details. So the first observation is, so the idea is that you reconstruct all of the projections by induction, more or less explicitly. So for n equals 1, then you don't have to do anything, because in this decomposition, if you look at the degrees, the only component that occurs is q equals 0, so you're done already. If n is larger than 1, then you can decompose Cn into a proper or normal sum of complex spaces and use the induction assumptions on these subspaces. So in these subspaces we have such a decomposition. So what you can do now is plug in sums of functions defined on these subspaces. This is now separately an invariant valuation in each argument. And so it first decomposes according to the degree of homogeneity, because of the homogeneous decomposition. And then you have this decomposition from the induction assumptions by this degree of complexity. So, and you get certain unique continuous functionals that are now defined on the space of convex functions on E times the space of convex functions on F separately. And these are valuations. And in fact, because the projections are continuous, this map, this associates to mu, this special component, this now depends continuously on mu. So now you can go back to the dense subspace of valuations that are constructed from your measures, and you can check what happens with those. And you notice that this component here should actually correspond to the degree P1 plus P2 component. So this is how you separate these different components. And now that you have those, you can try to reconstruct suitable densities from this functional. And this is, for this, you plug in suitable functions, suitable families of functions, and try to explicitly invert the transform that you get from that. And so you can explicitly reconstruct these densities in most cases. Now that you have those, you can integrate them with respect to the measures. And this gives you a map from the space of k-homogeneous valuations, the WN invariant, to these special components. Yeah? Because all of these measures, theta and epsilon, give you valuations in these components. And now the main work starts. You have to check that everything in the whole construction somehow depends continuously of the valuation that you throw in the beginning. So you have to check that the densities lie in the correct spaces, and then that the reconstruction procedure depends continuously on the valuation. Because if everything works out, then you get some continuous map that should be your projection. And how do you verify that it is a projection? Well, it's continuous, so you can verify that it is the projection by just looking at what it does on the dense subspace that you already know, where you have this decomposition. And then you're done. You have your projections, and you get this decomposition of your space. Now that you have this, it becomes much easier to get to the actual classification result, because now you've already separated all of these components, and now you can just work individually with these components and get this additional characterization results of these individual components. And then you're done. Thank you very much for your attention.